There is a machine the Soviet Union built that should not exist. A computer with no circuits, no electricity, no programming, no binary code. Yet it solved equations so complex that even early digital computers struggled to keep up. It designed canals across deserts. It helped build railways on melting permafrost. It modeled the freezing depths of Antarctica. It guided rocket engineers and geologists, and it did all of this with flowing water. For 50 years, this impossible machine quietly shaped Soviet infrastructure. Today, only two remain, locked inside a museum like relics from a forgotten timeline. This is the strange, nearly unbelievable story of the Lukyanov Hydraulic Integrator, the computer that ran on water, outsmarted nature, and refused to die. In the early 1930s, the Soviet Union faced a problem that nobody could explain. Concrete structures kept cracking every winter. Bridges, dams, walls, all fracturing in ways that made no sense. Engineers blamed poor materials. Workers blamed faulty construction. Officials whispered about sabotage. But none of these theories held up. One man, Vladimir Sergeyevich Lukyanov, noticed something everyone else ignored. The cracks followed patterns. Patterns tied to how heat escaped from the concrete. Heat moved unevenly. Some areas cooled fast. Others held warmth longer. This created invisible internal stresses and, eventually, fractures. To diagnose the problem, engineers needed to solve partial differential equations describing heat flow. Equations that were brutally complex. Equations that took weeks of manual calculation. Equations that most engineers simply gave up on. And there was one more challenge. The kind of digital computers that could handle these equations didn't exist yet. So Lukyanov did something that sounded ridiculous. Something nobody had ever done. He asked a question so strange, it almost sounded like a joke. If heat behaves like a flowing substance, could a flowing substance be used to simulate it? Heat spreads. Water spreads. Heat seeks equilibrium. Water seeks equilibrium. Heat diffuses through concrete. Water diffuses through pipes. The mathematical similarities were undeniable. Lukyanov realized he didn't need a digital computer. He didn't need electricity. He didn't need binary logic. He needed plumbing. So he began building a machine out of tanks, glass tubes, valves, reservoirs, pressure chambers. A maze of pipes that looked more like a failed chemistry experiment than a computer. Each tank represented a variable. Each pipe represented a mathematical relationship. Each valve represented an operation. And the height of water? That represented numbers. When you opened the valves, water rushed through the system, automatically performing the calculations. Not symbolically, not digitally, physically. The laws of fluid dynamics were the processor. When the water settled into equilibrium, the equation was solved. To record the results, Lukyanov added a mechanical plotter. As water levels shifted, a pen traced a curve on paper, a graph of the solution forming in real time. In 1936, the first hydraulic integrator was complete, and the world's first water-powered computer was born. It was accurate within 1 to 3%, stunning precision for the era. More accurate than many mechanical and electrical machines. But the wildest part? This thing wasn't just a calculator. It could simulate reality. By the 1940s, Lukyanov refined the design into a reconfigurable modular system. By the 1950s, the Soviet Union began mass-producing it. Universities taught students with it. Research labs depended on it. And soon, the machine proved it could do something digital computers of the time absolutely could not. It could predict the behavior of physical systems with extraordinary accuracy. Groundwater seepage, soil freezing and thawing, heat transfer in metal, pressure inside ice sheets, fluid flow in porous rock. If nature did it, the hydraulic integrator could copy it. The Soviets now possessed a machine that could run reality before construction began, and they put it to work on some of the most ambitious megaprojects in the country. The Karakum Canal was one of the Soviet Union's most daring projects, a massive waterway cutting through the scorching Turkmen Desert. But there was a deadly problem. Water poured into sand simply disappears. It seeps downward, sideways, everywhere. If engineers couldn't predict exactly where the water would escape underground, the canal would fail catastrophically. Early electronic computers couldn't handle such an enormous simulation. But the water computer could. Engineers configured the integrator to mimic desert soil. They opened the valves, water flowed through the pipes exactly the way real groundwater would move under the canal. Where the water in the machine vanished, the real canal would lose water. Where water pooled, the canal would need reinforcement. The canal succeeded because a box of glass tubes predicted how an entire desert would behave. Next came a problem that was the exact opposite: not too much heat, but too little. The Baikal-Amur main line, a railway through Siberia, crossed vast fields of permafrost, frozen ground that becomes dangerously unstable when thawed. If heat from the sun, from trains, or from underground energy seeped into the soil, the entire track could collapse. Engineers needed to know exactly how heat would spread under the rails. Digital computers of the time couldn't simulate it. The mathematics was too complex. But Lukyanov's water computer had been invented for this exact problem: heat flow. They built a model of Siberian soil inside the machine. They let the water run. When the levels stabilized, the integrator revealed where thawing would happen first. Engineers added insulation, drainage, and reinforcements in precisely the right locations. The railway survived because the water computer showed where Siberia would melt. The more scientists used the hydraulic integrator, the more they realized it was incredibly versatile. In Antarctica, it simulated heat flow inside ice sheets, making it one of the earliest tools for climate modeling. Rocket engineers used it to understand heat movement inside engines, vital for preventing catastrophic failure. Geologists used it to simulate how oil and water moved through underground rock formations. In every case, the digital computers of the time were too slow or too limited. The water computer? It just needed a new pipe configuration. It was a physics engine decades before the term existed. By the 1960s and 70s, digital computers were everywhere. They were faster. They were cleaner. They were the future. So why didn't the hydraulic integrator disappear? Because early digital machines were unreliable. They overheated. They crashed. They returned mysterious errors. They required teams of programmers. And they cost a fortune. The water computer had its flaws: leaks, clogs, mechanical hiccups, but they were easy to fix. A wrench, a cleaning brush, a bit of tape. It needed no coding, no operating system, no memory. Just water and a pump. It was cheap, simple, and shockingly robust. So it kept running, all the way through the 1980s. A water-powered computer outliving early digital ones sounds impossible. But it happened. Today, the hydraulic integrator is almost forgotten. Only 2 machines have survived. Both sit inside the Moscow Polytechnic Museum. Visitors walk past, barely glancing at them. They see a cabinet filled with empty glass tubes, not realizing those tubes once simulated deserts, ice sheets, oil fields, and rocket engines. They see a rusted frame, not realizing it once solved some of the hardest equations in engineering. The last survivors of a different kind of computing. One the world abandoned too quickly. For a brief moment in history, the most powerful computer in the Soviet Union wasn't made of silicon. It didn't run code. It didn't have a processor. It was made of pipes, pressure, and flowing water. A reminder that innovation isn't always digital. Sometimes the universe already knows how to compute. Sometimes you don't need a processor. Just gravity, just pressure, just fluid. Sometimes all you need is to open the right valve and let the answer flow.